Understanding the universe and the vastness of space is at the forefront of physics and astronomy research today. Everything from white dwarfs and red giants to neutron stars and black holes. But imagine trying to make sense of the cosmos before telescopes were even invented. Well, between the 9th and 14th centuries, scholars from the Islamic world consolidated and refined the astronomy of earlier civilizations and came up with ideas that have deeply influenced astronomy right through to the present day. I'm Jamal Khalili, a British professor of physics, but born in Baghdad, and I'll be taking a look at modern-day astronomy and navigation and exploring the contribution made to these fields by the scientists of the Golden Age. Why were the scholars of the Islamic world so interested in astronomy? One reason is for navigation. People have been using the sun and the stars to find their way around for thousands of years. I'm heading into the desert outside of Doha in Qatar, and I'm using the sat-nav to help me. So in a sense, I'm still looking to the sky to navigate. Well, now it's getting late and I think I'm really lost. So I think I'm going to have to call someone to help me. Ali Sultan al-Hajri is a Qatari businessman and Bedouin with a deep knowledge of the desert and the Bedouin way of life. Navigation has always been a crucial skill for the Bedouins. So, Ali, as a Bedouin, how do you find your way around the desert so accurately?
There's two types. During the day, we know by the sun if it's this side or this side. If it's in the middle, sometimes we get lost. During the night, we go by stars.
You're familiar with, with the night
Al-Jadi,
sky,
which is in the north.
Yes.
It's always there. And we have some other names like Sahel, Joza, Thuraya.
These are all famous star names. They're all Arabic names, aren't they?
Yes. And we know the direction by the
stars.
By the stars. Bedouin, by the way, they have a very unusual sense of direction. It's in their DNA. And when I'm driving, walking, I know. If you just stop me instantly, said, Ali, where is north? I will say, this north, immediately. Yes, of course. Let's go now. Have a seat.
Thank you. As well as navigation, astronomy was also important for the measurement of time. For example, the Islamic calendar is a lunar calendar where the months are determined by the phases of the moon. During the Golden Age, astronomers studied the movements of the moon to predict the calendar more accurately. The 12 months making up the Islamic year are shorter than the Earth's orbit of the sun. So, Islamic months and religious observances like Ramadan move from year to year.
The lunar calendar is shorter by 11 days. And every 33 years, about, it's a cycle. For example,
between the lunar and the Gregorian?
Yes. For example, if Ramadan starts now in January, which is in the middle of the winter.
Yes.
After 33 years, it will come back again in January.
Ali, I think these days even someone like me can pretend to be as knowledgeable about the night sky because I want to show you this app I have on my tablet. You see, it shows,
wow,
it maps the night sky.
Yes, I know. Let me see if I can see the North Star.
You know that's north, do you?
Yeah, it has to, that's it.
Polaris.
That's it. So, I thought they call it the North Star.
Well, that's another name for it, but it's
wow.
You see, I don't need to know that's north. I can hold that app up, and if I know the North Star is there,
then you know the directions, right?
Then I should know my directions. This app on my tablet allows me to scan the night sky and identify the stars and planets. It's the modern-day equivalent of the ancient star chart, known in Arabic as a Zij. Now, in the early 9th century, the Abbasid Caliph al-Ma'mun, the ruler of the powerful Islamic empire, was a man obsessed with scholarship and learning. And he commissioned a group of astronomers to produce a new Zij. Now, they already had the astronomical tables of the ancient Greeks, but they were tasked with improving on them, correcting errors and making more accurate measurements. They produced a new star chart that became known as al-Zij al-Mumtahan, or the verified tables. Here in Istanbul, I'm standing on the very edge of Europe, but I can look across to Asia on the other side of the Bosphorus. From the 7th century, the Islamic Empire and its people spread out of Arabia to Asia in the east, all the way to Spain in Europe. But to conquer so much land, they had to be great navigators. Throughout antiquity, maps were drawn by hand and relied on travelers' accounts. For example, before the Golden Age, the Greek astronomer Ptolemy had compiled lists of over 8,000 coordinates detailing the positions of oceans, landmarks, and cities. In the 9th century, the ruling Caliph of Baghdad, al-Ma'mun, commissioned a group of his scholars to make a new map of the world and to improve on Ptolemy's data. At Istanbul's Museum of the History of Science and Technology in Islam, Dr. Detlef Quintern is a scholar of ancient geography. Together, we're looking at al-Ma'mun's map.
This map dates back to the reign of al-Ma'mun in the first third of the 9th century, the flourishing period of Arabic Islamic science in Baghdad.
I guess what was different about it is that they wanted to improve on the Greeks' maps.
Absolutely. They measured the longitude and altitude of Baghdad.
And of course, the Baghdad didn't even exist during the time of Ptolemy. So
yes.
They had to, I guess, add all these new cities, Mecca as well.
Mecca as well, absolutely. So there were a lot of more precise coordinates.
Al-Ma'mun's map was from the very early years of the
Right.
Golden Age.
Right.
Here we have an example of a map several centuries later, the culmination of geography in the Islamic Empire. It's a map of the world, but it's not one that I recognize. I don't see any countries that look the shape they should look.
All Arabic maps are southwards oriented. So Africa is always on the top.
At the top. So in fact, so this is upside down.
It is upside down. We
Let's
can
see if we
turn
can
it.
Recognize it.
Yes, right.
That's better. Okay, so now I see Arabia and the Mediterranean. So what was new or different about this map?
You can see the shape of the Mediterranean and the shores, and it becomes more precise, even also the shape of the Caspian Sea.
And it was this map that then, of course, led on to advances in Europe.
Absolutely.
The maps that were so important for navigation.
Yes.
So how did the map makers of the Golden Age determine such detailed measurements? They used a versatile scientific instrument called an astrolabe. I've come to the Museum of Islamic Art in Qatar, where among their many artifacts they have a wonderful collection of astrolabes spanning back almost 1,000 years. And I'm hoping that one of their curators, Dr. Noor Khan, is going to tell me what's special about a couple of them. The lovely thing about astrolabes, Noor, is that before the invention of the telescope, these devices were incredibly important. How far back do astrolabes go? When were they first invented?
Historians say they go back to 300 BC in Greece.
And the word astrolabe comes from the Arabic astrolab.
Astrolabe, exactly, which is originally from the Greek, to grasp the stars, because actually what you have here is a handheld model of the sky.
Early astrolabes offered only a few functions. But during the Golden Age, astronomers developed more sophisticated astrolabes. This one is very, very elaborate, and it's multifunctional.
Astrolabes in many ways were the computers of their day, and they basically served a number of purposes. You can use it to find the time of day or night. You could decide prayer times, you could navigate, you could measure the heights of buildings or distances. There are all sorts of uses.
You could do all of that with this disc, because of course these are all moving parts.
Yes,
is it possible to take it apart and see the components?
We can.
A single map of the stars would only be correct for one location on the Earth. But these sophisticated astrolabes were designed to work in many places.
A later astrolabe, such as the 17th century astrolabe, had a number of different plates engraved on both sides, and each one could be used for a different city to tell the time, to plot the motions of the stars, or whatever it is that you needed your astrolabe to do.
So wherever you were in the world, you'd use the appropriate map of the sky.
Absolutely, yeah.
With all its intricate markings and measurements, to use an astrolabe, you already needed a good working knowledge of astronomy.
So here we have 5 plates inside. You then adjust this, the reed.
I see. So you put the right plates in position.
Yes.
You take a measurement of
a particular star or of the position of the sun. And then you adjust the reed over the correct plate, and that gives you a map of the sky where you are.
Astrolabes were powerful tools for astronomers in the Golden Age, but modern astronomers have access to a vast array of instruments, such as this, the Lovell Radio Telescope in Jodrell Bank in the UK. During the Golden Age, astronomers would come together from across the world to cooperate, and that way of working is still embedded in astronomy today. Astronomers working with this telescope often collaborate with other telescopes and astronomers internationally. Unlike a conventional telescope, it doesn't capture light through a lens, but rather uses a massive dish that collects very weak radio signals from deep in space, allowing us to map the universe in ever greater detail. Now, Tim, because the Lovell telescope is a radio telescope, it's seeing the sky in a way that we can't see.
Yeah, I mean, it basically sees the invisible universe. I've got a picture here of what the Lovell telescope sees. If we could see radio waves, this is the way the sky would appear. That's our Milky Way galaxy. What we see in that picture is not the stars that we see with our eyes, it's the stuff between the stars. One of the really interesting things, I think, is looking at planets around other stars. There's a picture here of a young star in our galaxy called HL Tau. The star is at the centre, and then around it there is a disk of gas and dust. But the interesting thing here are the dark circles. We think that they're formed by planets that have formed inside the disk, and as those planets circle around, they sweep up the gas and the dust and they leave behind these empty gaps.
It's amazing, isn't it, that we're not talking about planets going around our own sun in our system. These are planets going around distant stars, hundreds of light years away.
Yeah, and many, many thousands of these planets, many billions, in fact, in our own Milky Way galaxy.
And you mentioned that image was taken by another telescope. This is part of a larger collaboration.
To get these sort of sharp views, we have to combine signals from many telescopes spread across the country and even across the planet itself. So this shows us all the locations of the various radio telescopes across Europe, out into China, down into South Africa, and we even link up these telescopes with a Russian spacecraft that's orbiting the Earth. So we end up making telescopes the size of the planet or even larger than the planet.
Because they're all contributing their own data.
So a single telescope will give you a blurred view. By working together with these telescopes in these other countries, we all joined forces to make this planet-sized telescope that shows us the detail.
This idea of scientists working collaboratively together, particularly in astronomy, is something that goes back 1,000 years to the Golden Age. It was in Baghdad around the 9th century when we first start to see astronomers working in groups to solve big problems in astronomy, something that the Greeks didn't do, something that only really emerged in the Golden Age and has survived so successfully to this day. one of the most important observatories of the Golden Age was called the Maraga Observatory, built in 1259 in Persia for the great astronomer Al-Tusi. When the Mongols invaded, they captured the mountain fort of Alamut, where Al-Tusi worked. Not only did he convince the Mongol general Holako, or Heluga Khan, to spare his life, he convinced him to build him a new observatory. In return, Al-Tusi promised to provide the general with his astrological charts so that he'd know what day to go to battle. The Maraga Observatory became the most important of its day and a great hub for international scientific collaboration. Of course, what's great about the Maraga Observatory and the astronomers that worked there isn't the observations they made. They didn't have telescopes, but it's the mathematical tricks they developed that will be influential in astronomy for centuries to come. And I wanted to show you something here. So this is a diagram from Tusi's work. People like Tusi, when they were looking up trying to explain how the stars and planets moved, they were trying to develop the maths to make it sensible. And of course, you know, they were using the Greek model.
Yeah, which had got incredibly complicated, of course. The Greeks believed that the Earth was at the centre of the solar system. And in order to make the mathematical model fit the observations of the way in which the planets appeared to move on the sky, they had to put all these ridiculously complicated features into the model.
It got very, very messy. Circles within circles going around other circles.
It did, yeah.
And that's where Tusi's genius comes in, because this diagram, the Tusi couple, simplified a lot of that. If I show you what's supposed to happen, you see this small circle going around the big one. If you trace a point on the perimeter, it's moving up and down in a straight line. And that turned out to be a very useful trick that simplified a lot of that complicated maths.
Yeah.
But what's really fascinating, compare this text written in Arabic with this one. It's an identical one, but written in Latin. And what's fascinating is the letters labeling the points follow the Arabic alphabet, not the Latin alphabet. So Alif, Ba, Jim, Dal, A, B, G, D. Clearly, whoever drew this knew about Tusi's work and the Tusi couple. Well, the man who drew this was Copernicus.
So this is Copernicus who came up with the idea that rather than the Earth being at the centre of the solar system, it was the Sun at the centre, and all the planets, including the Earth, revolved around it.
Revolved around it, and that's the picture that we have today. Copernicus was and is regarded as the father of modern science because of this great revolution. And yet what's so fascinating
is that this was built on Tusi's ideas.
Yes, so it shows the continuity of science. Copernicus owes this debt to these medieval astronomers from the Golden Age.
That's incredible.
Islam itself was a significant reason behind many of the early explorations and discoveries in astronomy during the Golden Age. There was a need to know the accurate time for prayer, the direction to face towards Mecca, and the dates of religious festivals according to the lunar calendar. Astronomical instruments like the astrolabe played a very important role in this. One of the requirements of Islam was to know which direction Mecca was in order to face towards it during prayer. Now, during the early days of the empire, it wasn't so large and this wasn't a problem. The scholars of the Golden Age were very proficient at map making. But as the empire grew and stretched from India in the east all the way to Spain and Andalusia in the west, it was much more of an issue because the scholars also knew that the earth wasn't flat. Now, why does this matter? Well, if you were, say, a Muslim in Cordoba, then facing towards Mecca, if you just looked at a flat map, would involve pointing roughly southeast. But on a globe, it's different. If I attach this string, one end to Cordoba and the other to Mecca, then you see the line actually takes you east to begin with and then curves down to the southeast. So it's not at all obvious without understanding that the Earth is a sphere. This meant that these scholars had to develop an area of mathematics called spherical geometry, which was exceptionally advanced for 1,000 years ago. But to use this spherical geometry, the scholars first needed to know the size of the Earth. The ancient Greeks had provided several estimates of this. Their method was clever but crude. It involved measuring the angle of the sun at a particular time of day and then walking in a straight line in a particular direction until that angle changed by 1 degree. All they then needed to do was calculate how far they'd need to walk for the angle to change by 360 degrees. That would give them the circumference of the Earth. The early 9th century Abbasid Caliph al-Ma'mun wanted to improve on this estimate, so he commanded a group of astronomers to repeat it. However, the method involved them trudging through the desert for over 100 kilometers, a method that was prone to error. 200 years later, in the 11th century, the Persian astronomer al-Biruni came up with a much easier and more accurate method of estimating the size of the Earth. But it did involve climbing a mountain that looked out over the horizon. Al-Biruni was a prolific scholar who even debated about whether the Earth was moving. He explained how to work out the size of the Earth in his book on the determination of the coordinates of cities. First, he measured the mountain's height. Al-Biruni then had to climb to the top of the mountain, and armed with an astrolabe and a plumb line, he then measured the angle of dip from the horizontal down to the distant horizon. Now, this was just ½ a degree, so he had to be incredibly precise. But armed with this information, he could then use some more clever geometry to calculate the circumference of the Earth. Let me show you. Imagine this circle is the Earth, and this is Biruni's mountain. Now, looking across horizontally, he measured the angle of dip to the horizon, this angle here. Now, if you draw two lines, one through to the center of the Earth from the mountain and the other from where the line touches the horizon, you end up with a right-angled triangle. Now, Biruni knew that the angle he'd measured is the same as this angle inside the Earth. Armed with these two pieces of information, the size of this angle and the height of the mountain, he was able to use geometry to work out the radius of the Earth. Multiplying this number by 2 pi gives him the complete circumference. He got to within 1% of the accurate value we know today, about 40,000 kilometers, which is pretty remarkable. It's easy to think that astronomy went to sleep after the ancient Greeks and didn't wake up again until Copernicus in the 15th century. But developments in astronomy continued in Spain, the Middle East and Central Asia throughout medieval times. The Renaissance scientists of Europe who created modern astronomy were building on the work of people like al-Biruni and al-Tusi, who in turn were building on the knowledge passed over to them from earlier civilizations. Today, in the 21st century, international teams of scientists are still looking to the stars and mapping the cosmos using ever larger telescopes. But we must remember that they owe a huge debt of gratitude to those astronomers of the Moraga Observatory.